Okay, trig is all about triangles. Triangles are three angled figures, so let's get started by talking about vocabulary for angles. An angle starts from a fixed point called the vertex. It has an initial side, and then the measure of the angle is from the initial side to the terminal side. The angle is assumed to go in a counterclockwise rotation. Counterclockwise counts as a positive angle direction. So starting from the positive x-axis as the initial side, you could go positive around to the positive y-axis and on around, or a negative angle would open and start with the terminal side going into quadrant 4. So positive angle has this counterclockwise rotation. A negative angle is then the other direction, a clockwise rotation, and we could measure the same angle either as that positive angle alpha that we gave in the first slide, opening in a counterclockwise direction, or from the initial side to the same terminal side, we could also specify that angle by giving the negative angle. Angles don't have to open with the initial side, the positive x-axis, but we'll say that the angle is in standard position if it does. So sort of see the angle as sitting on a set of axes that you could draw in, put the origin where the vertex is, lay it out so that the initial side of the angle goes in the positive x direction, and then see where the angle goes. This is written as this would be a positive measure of the angle theta from the initial side in the standard position. That's the positive x-axis. The terminal side of this angle happens to be in quadrant 2. That's fine. Well, angles that go around a full revolution from 0 all the way around is a complete revolution, and the conventional scale for angles to do that is 360 degrees. That was something that somebody declared by fiat, that a full rotation should be 360 degrees. It's kind of like saying how big a gallon is or how long a meter is. It is something that culture settles on and makes it easy to convey information back and forth, and that's the scale then for degrees. A good thing about 360 degrees for people who don't like fractions is 360 degrees has lots of small factors. You could divide it evenly by 2, 3, 4, 5, 6, 8, 10, 12, lots of small numbers, and that means that you can subdivide a full revolution into an integral number of parts, and quite often end up with, without fooling with fractions, have a whole number of degrees in each part. So with 360 degrees as a full revolution, it's worthwhile looking at some of these partial ways around, and maybe the most important one is to go a fourth of the way around. A fourth of the way around would measure a fourth of 360 degrees. That's 90 degrees, and so a 90-degree angle is measures a fourth of the way around. That's called a right angle, and you see this little right angle completion here to make a little square to remind you that if you know that if it's a right angle, then you can indicate it with that in the picture. In general, we'll look at a circle of arbitrary radius r and set up the angle so that the angle has its vertex at the center of the circle. If that happens, it is a central angle. And now we're looking at an angle and at the arc on the circle that the sides of the angle subtend, that the sides of the angle span. And that is a way of linking arc length to angle length. And if you do it so that the arc length matches exactly the radius of the circle, then you've specified a particular angle that is, in some sense, a very convenient measure, and that's called 1 radian. Here's a picture to show you that. So we've got a circle of radius r, and think about this r as being maybe a piece of string, and you wrap it around the circle so that this distance from here curving around to here matches the distance from the center out to the circumference. So this length matches that length, and if you set it up that way, radius matching the arc length, then the angle that determines between an initial side and a terminal side, so that this arc length spans a distance that matches the radius of the circle, that makes an angle of 1 radian. That means that if you've got angles measured in radians, so that you could take this as a scale and now make bigger angles or smaller angles and calibrate it with this as the size 1, and then maybe bigger than 1, less than 1. If you do that, then you can link arc length with the size of the angle directly. It's a very simple relationship. It is this: if the angle is measured in radians, the circle of radius r has a radian, and the circle of radius r spanning an arc over this angle theta, the arc length s is given just by r times theta. If you ever wonder why in the world you need to keep track of different ways of measuring angles, why should you do degree measure or radian measure, the essence of it's contained in this formula. Degree measure is great if you don't like fractions. Radian measure is great if you like to be able to scale immediately to arc length. Radian measure of the angle gives arc length just as a multiple of the size of the angle. Directly measured in radians, it's just a product, and that's a good fact to have, and it makes a lot of problems easier to understand with radian measure than they would be if you were measuring with degrees. One more point: this formula for arc length is applicable only when the angle is measured in radians. Okay, so let's talk about triangles. If one angle in the triangle is a right angle, then it's a right triangle. You can keep track of the labeling. Here's the right angle. Opposite the right angle, the word for the longest side of the triangle is the hypotenuse. And the other two sides, the sides that are adjacent to the right angle, are the legs of the triangle. So we've set things up so that this maybe is the initial side of this 90-degree angle. This is the terminal side. Initial side and terminal side are the two legs of the right triangle, and this third side, the side opposite the 90-degree angle, is the hypotenuse. So the relevance of this to an angle is, anytime you've got an angle, initial side, terminal side, the angle spanning in between, hiding in there is a right triangle. All you have to do is drop a perpendicular. Let me do that. And the perpendicular could be one leg of the right triangle. This could be this side, the horizontal side, the initial side of the angle could give another leg of the right triangle. And then the hypotenuse could be measured out along the terminal side of the angle. This is standard labeling. You'll see right triangles like this quite often, laid out so that there's a horizontal leg kept track of with A, a vertical leg kept track of with B, and the hypotenuse kept track of with C. With those three sides, you can write down ratios, and the ratios of the sides don't depend on the absolute lengths of the sides. If you scale this and make it a bigger triangle or a smaller triangle, but keep this angle the same and keep the right angle here, the ratios of the sides won't change. Double C and B doubles. So the ratio B over C has a factor of 2 doubled top and bottom, so that the ratios itself, that 2 cancels and its value is the same. So think about it as a problem in putting pieces together. If you want to build ratios so that you keep the ratio the same, independent of scale, there are 3 possible choices you can make for something to go on top of the ratio. And having picked that, you don't want to pick the same value on the bottom. That would make the ratio 1. So something interesting, different, would be one of the others. 3 on top, then 2 different ones to put on the bottom, and there are 6 in all. Every possible ratio defines a trigonometric function. Here they are, all 6 trigonometric functions, and you can keep track of them by their name: sine, cosine, tangent, cotangent, secant, and cosecant, or their abbreviation. I like to think of this as their nickname: sine, cosine, tan, cotangent, secant, cosecant. And here is the ratio of sides that go with those. Again, let me go back to the triangle to remind you. A is the horizontal side, the side adjacent to the angle. B is the vertical side. The way I've drawn this in, it's the side opposite the angle theta. And C is the hypotenuse. So sine is opposite over hypotenuse. That's B over C. Cosine is adjacent over hypotenuse. That's A over C. Tangent is opposite over adjacent. That's B over A. You might have noticed that this lecture was titled this funny looking word Sohcahtoa, and Sohcahtoa is there to remind me of those values. S in Sohcahtoa is sine. Sine is opposite over hypotenuse. Sine, opposite hypotenuse. Cosine, adjacent over hypotenuse. Tangent, opposite over adjacent. And then the other 3 trig functions, cotangent, secant, and cosecant, are given in terms of reciprocals of values we found already. B over C is the reciprocal of C over B. So cosecant's the reciprocal of sine. C over A is the reciprocal of A over C. So secant's the reciprocal of cosine. And A over B is the reciprocal of B over A. So cotangent is the reciprocal of tangent. Interesting things to have. So if you can do the triangle geometry, you can recover values for all 6 of these trig functions. Here's an example. Here is a right triangle given, and I have enough information here to determine everything that I need. I'm given C is 13, and relative to this angle theta, the side opposite theta, this vertical side, I'd call that B, is 12. I don't know the adjacent side to the angle, so let's get that first. I can get that from the Pythagorean theorem. Let's see what we know. The hypotenuse is of length 13. Side B, the side opposite the angle, is of length 12. So a squared plus b squared equals c squared. That's the Pythagorean theorem. I know b, I know c, so I can solve for a. Plug in 12 for b, 13 for c. Solve that for a, and a squared is 13 squared. That's 169 minus b squared minus 144. 169 minus 144 is 25. That happens to be a perfect square itself. So a could be assigned the value of 5. So let's look at what we've got in our triangle. We've got a, 5, b, side opposite, is 12, and c, the hypotenuse, is 13. Let's put together all the ratios. Sine is opposite over hypotenuse. That's b over c, 12/13. Cosine is adjacent over hypotenuse. That's A over C. That's 5/13. Tangent is opposite over adjacent. B over A is 12/5. Now let's get the reciprocal ones. Cosecant is the reciprocal of sine, so 13/12 is C over B. Secant is the reciprocal of cosine, so C over A is 13/5. And cotangent is the reciprocal of tangent. Instead of 12/5, it's 5/12. All 6 ratios arise as values of the trig functions that you can calculate knowing the sides of the triangle. Well, let's see some relations. With so many bits of information, all 6 of these values built from 3 numbers, 6 ratios, there have to be some redundancies that you could exploit, some places where you've got extra information you could use to check. So for example, from the triangle labeled with A, B, and C in the Pythagorean theorem, a squared plus b squared equals c squared, if you take this equation and divide through by c squared, then it gives the quantity, if I want to write it that way, b over c squared plus a over c squared is 1. Now, b over c, that ratio was opposite over hypotenuse. That's the sine of this angle. And a over c is adjacent over hypotenuse relative to this angle. That's the cosine of the angle. So we have a relation between the sine function and the cosine function. Very important relation called the Pythagorean identity, that no matter what the angle theta is in this right triangle, the Pythagorean theorem guarantees that sine squared of theta, the ratio that defines the sine of theta squared, plus cosine squared of theta, those two values added together always equal 1. One more, excuse me, one more bit of geometry that's worth pointing out. If the angle is, if it's a right-angled triangle, a right triangle, then the sum of the angles is 180 degrees in any triangle. If 90 degrees is accounted for by one of the angles, then the other 2 angles have to together make up the other 90 degrees, the rest of the degrees in the triangle. Relative to this angle, this is side adjacent and side opposite. Relative to this angle, the same numbers work, but they have different interpretations. Relative to this angle, this would be the side opposite this angle, and this would be the side adjacent to this angle. That means if you wanted to calculate the sine of this angle, opposite over hypotenuse, that ratio b over c corresponds to adjacent over hypotenuse relative to this angle. Well, this angle and this angle together add up to 90 degrees. This angle and this angle are complementary angles. So, what we see is the same ratio describes a trig function of one angle and the cofunction, sine compared to cosine, cosine compared to sine, tangent compared to cotangent, the cofunction of the complementary angles. That is summarized by this result, the complementary angles theorem, that cofunctions of complementary angles are equal. So here's an interesting bit of trivia. You wonder why it's called cosine, cotangent, cosecant. It's this theorem that says the co in cosine is short for complementary. The cosine is the complementary angle sine. That's what this theorem says, and it works for the other trig functions as well. So that's an interesting bit of trivia to end this on. See what you think about the homework problems and the book's presentation on this material.